Wonderful stuff, and welcome everybody to the final student presentations for the day. So we've got a couple of excellent presentations coming up, and we're going to start off here with Eric on his presentation, Happy Transformer.
Great, thank you very much. So yeah, today I'll be presenting Happy Transformer. Happy Transformer is an open source library that allows anyone, even beginners, to implement state-of-the-art natural language processing models using only a few lines of code. Now, since its release, it has achieved over 6,000 downloads. It has been starred 57 times, and it has even been used by top researchers to create models for a paper that was accepted into the second best conference in the world for computational linguistics, according to Google Scholar. So we're going to get to all of this and more, but first, let's talk about what is natural language processing. Natural language processing is an intersection between linguistics and computer science, where practitioners create models that are able to analyze, understand, and even generate language. A good example of this would be machine translation, for instance. And like for many fields, deep learning has completely revolutionized the field in recent years. But there's been one specific area that has been getting lots of attention, and Professor Bengio talked a lot about it during his keynote address, which was the concept of attention. And Professor Bengio mentioned transformer models. So transformer models were first proposed in 2017 by Google. And since then, they have completely revolutionized the field of NLP. Now, I won't get into all the details about how these models work. It's very technical, but I will talk about their capabilities. So typically, language models are evaluated on something called the GLUE benchmark, which stands for the General Language Understanding Evaluation Benchmark. And this benchmark is comprised of several tests, and the language models do each test individually, but their score is averaged. So it's thought of as being a robust way to gauge how well a language model truly understands language. And since the release of transformer models, companies have been creating incredibly powerful models that have been doing very well on the GLUE benchmark. Currently, the top models outperform the human baseline on the GLUE benchmark. So I'll say that again, the top language models in the world outperform the human baseline. Absolutely incredible. So my team over at QMind, we wanted to use some of these transformer models, and there are many transformer models available, such as BERT, which Google released, and Facebook AI has been releasing some, Microsoft AI. For the audience, many of you have probably heard of GPT-2. That's a good example of a transformer model that specializes in generating text. The creators of GPT-2 were scared about releasing it because they thought it might have potential for misuse due to how powerful it is. So there are lots of very powerful transformer models that these companies are releasing to the public that are already trained. My team at QMind, we wanted to use some of these models. We wanted to get practical experience using these models. So we were attempting to solve the Winograd Schema Challenge. Without getting too much into it, the Winograd Schema Challenge can be thought of as a better alternative to the Turing test. And the Turing test, of course, I'm sure many people in this audience know, is a test to determine if an AI is truly intelligent. So the Winograd Schema Challenge is a better version of this test that's more quantifiable. So my team, we were working hard on creating a solution for this challenge, but we were running into lots of problems. It was difficult. It was very difficult to implement transformer models using the current systems in place. We were successful in some areas, but we were running into lots of difficulties. And when we went on forums, we noticed that many other people were having difficulties. So this led to us identifying the problem that there needs to be an easier way to use transformer models. And we had a few other realizations, like how there's a large demand for transformer models due to how powerful they are. We realized that only experts were able to properly use the current systems due to how complex they were. And we also, of course, realized that AI and NLP in particular is a rapidly growing market. But most importantly, we realized that we can actually solve this problem, because although we were having difficulty, we were making some progress. We were learning how to implement transformer models. So then Happy Transformer was born. Happy Transformer is a Python package that allows users or programmers to implement transformer models using only a few lines of code. And there are several available transformer models like BERT, Roberta, ExcelNet. Many of them are named after Sesame Street characters, which is kind of funny. And there are also several pre-trained models for mask word prediction, text classification, next sentence prediction, question answering. There's lots to get to, so I won't cover what exactly these all are, but these are fundamental NLP tasks. So using Happy Transformer, you can fine-tune these models for various tasks with using very few lines of code. And we, of course, we published this package to PyPy, which is the main distribution system for Python packages. So you can install Happy Transformer with one line of code. Just pip install Happy Transformer. It's in your environment. And since its release, it has achieved over 6,000 downloads from people of all skill levels. And soon I'll be getting to some of the more advanced use cases, but it's also nice to hear how beginners are using it as well. But both are equally good in different ways. And we wanted to show the world how capable Happy Transformer really is. So we competed in a Kaggle competition. For those of you who don't know, Kaggle is this online platform where people can compete in open competitions. There are experts who compete in these competitions along with beginners. So we competed in a text classification competition where we had to indicate if a tweet was referring to a natural disaster. And using just a few lines of code, we achieved results that placed us in the top 1.5% at the time of the Canadian Undergraduate Conference for AI. And at that time, there were over 2,800 competitors. So this shows that Happy Transformer accomplished what it set out to do, which is to make it easy to implement state-of-the-art NLP models, since it only took a few lines to get top results. And I was very pleased when I was emailing the first author. I was emailing Bill Lin about some of his work, and he used Happy Transformer to create and train the models for a very interesting paper called NumerSense, Probing Numerical Common Sense Knowledge of Pre-trained Language Models. So what his team discovered is his team discovered that you can fine-tune language models to have a better understanding of numerical common sense. So for example, if I asked you, dogs have blank number of legs, you know, blank is 4 due to common sense. But his team discovered, well, first of all, that it's very difficult for language models to do this, but he also discovered that with fine-tuning, there could be slight improvement in the ability for language models to perform this task. And it's a very good paper. I recommend you all check it out. And the paper was accepted into the second best conference in the world, according to Google Scholar, under the computational linguistics category called the Conference on Empirical Methods in Natural Language Processing. So this conference is coming up and his paper was accepted into it. So it's great to see that Happy Transformer has been used in real world research. So in summary, transformer models are incredibly powerful. Like I showed in one of the early slides, their top transformer models outperform humans on the glue benchmark. But however, they are very difficult to use. Like currently, the main method for implementing transformer models is to use the Hugging Face transformer library, but the documentation is very hard to understand for beginners. So to solve, and even intermediate people as well. So to solve this problem, we published a Python package called Happy Transformer that allows anyone to implement transformer models with just a few lines of code. And we used this Python package to compete in a Kaggle competition where we placed in the top 1.5% using just a few lines of code. And this Python package went on to be downloaded over 6,000 times and has been used by top NLP researchers to create their models. So now, for people in the audience, if you're ever interested in doing NLP research, I recommend you check out Happy Transformer and let me know if you need any help using it, but it's fairly simple to use. So Hopefully some of you in the audience might use it for future research. And if you do, please let me know if what you produce ever gets published or ever makes an impact. So thank you very much. Okay.
Thank you very much, Eric. Excellent presentation. And like I said earlier, anyone who has any questions, you can post them in the chat at any point, and we'll be able to get to them all after the next presentation. Next, we have Zhendong, has the second presentation coming up. Do you have your slides all on there? I'll give you a second to load them up.
Can I share my screen now?
Yep. There we go.
So can everyone see my slide?
We can see, oh, there we go, network-based, there we go, perfect.
Good.
It's come up. So I'll give the floor to you.
Okay, thank you, Alex. Hello all, my name is Zhendong from Computing at the Queen's. I'm thrilled to present one of the recent research from our lab. And it is called the network-based subject portrait approach, or portrait network in short. The secret of life is encoded in our genome. Since the availability of the human genome in the early of this century, tons of human genetic research have provided pieces of evidence indicating many human diseases, especially complex disease, are rooted in the genetic backgrounds of the patient. The genetic material that we received from patients is DNA. Through complex biological process, DNA produces mRNA through transcription, and mRNA is the blueprint for assembly proteins, which can be understood as a string of amino acids. The string folds into protein structures and extend the effect on the phenotype outcome, such as height, hair color, the risk for a type of disease, just to name a few. Any mutations in human genome may introduce perturbation in the interaction between proteins and eventually alter their downstream activities and the risk for disease. As you can see on the right, mutations may alter the structure of a protein and block the interface that bring together two proteins. If two proteins cannot bind with each other or with less efficiency, this may lead to abnormality of biological activities, cell death, or even trigger the disease onset. Today, I will present the following content to demonstrate the current progress on the portrait network model. I will first present how genetic mutations contribute to disease risk in the context of molecule interaction network, followed by presenting the limitations of the existing works. We will then discuss how our approach is crafted to address these limitations. At last, experimental results will be presented. Mutation results from evolution. One can receive mutations from inheritance or acquire through normal cell growth. But don't be panicked. Most of the mutations are harmless. Some of these mutations can lead to disease, which is represented in red color on the right figure, because it lies in a critical position in this network of biological molecule network. Whereas most of the mutations harbors in the human body are considered as passengers, which is represented in blue and yellow on the right. Because cell alone will not confer risk for illness, and passenger mutations can promote risk for disease by working together with other mutations. And finding these mutation combinations is computationally intensive because for human genome, it consists of multi-millions of genes. The network approach has been utilized to represent how genes work together to contribute to the risk of illness. The hope is to characterize the genetic architecture of complex disease using a network composed of two-way gene-gene interactions. Once we have a network of interactions, we can utilize existing well-developed network analysis methods to identify important genes in the network. Methods including network centrality measures such as degree centrality, page rank, a Google-developed network centrality measures. They will prioritize nodes in the network with regard to their influence on the neighboring node. However, there is an obvious gap between how the network of genes contribute to disease and the existing methods. That is, existing network analytical methods are originally developed for non-biological domains, in which edges in the network represent accumulable relations. For example, in social networks, the degree of a person can be interpreted as a popularity or influence, and clusters of persons means intensively connected social groups. This accumulable nature of network edges is not necessarily being correct in biological networks. In response to a genetic mutation at one gene, its interaction with the surrounding genes may respond differently. How exactly the genetic perturbation will propagate to the rest of the network is not explainable by using centrality measures alone. As you can see from the plot on the bottom right corner, proteins interact with their peers through different interfaces. A mutation may not necessarily block all of the interactions, so only a fraction of the interaction will be disabled as a result of mutation. This observation is quite obvious for biology domain, but is not embedded in the current network analysis. The poultry network consists of several steps. The first step constructs a network of gene-gene interactions, or comprehensive network. We utilize information theory-based metrics, specifically information gain, to quantify to what degree a pair of genes can explain the disease phenotype. The pairs of genes that have the highest degree of explanation will be utilized to construct the network. The second step is defined to solve existing limitations. For each subject in the dataset, the specific risk of each interaction will be recognized according to subject's mutations, making the comprehensive network into a sign network, with a plus sign indicates high risk and the negative sign indicates low risk. We then adopted the feature engineering step to summarize the subject networks into tabular data, which with each feature represents the number of plus degree minus the negative degree. To verify the contribution of the poultry network framework, we adopted cross-validation to verify its contribution to the predictive model and the feature importance analysis to find important genes that can explain disease phenotype the most. We will apply this framework to cancer genomics that we gathered from colon cancer patients and healthy controls from Newfoundland, Canada. 15 largest network components that consist of the most significant gene-gene interactions are selected to construct a comprehensive network. Approximately 1,000 genes are contained in the comprehensive network. First, we investigate how these mutations of genes outlined by the largest network components can explain the disease phenotype. As shown in the figure on the bottom right corner, the 98 genes from the largest network component, which is shown in blue bar, can provide a significantly better result than genes randomly withdrawn from a pool of 1,000 genes, which is shown in black bar. And putting the 1,000 genes together, the predictive performance is increased to 80%, which is shown in gray bar. And secondly, the feature engineering procedure can provide predictive advantages compared to making predictive tasks directly on the mutations of genes. As you can see on the right, the yellow bar indicates the predictive performance on the largest network component reinforced by the feature engineering procedure. It outperforms making prediction directly on the genes. And if the feature engineering process consider all 15 network components, all phenotype variations can be captured. As you can see, the red bar means all 15 network component is considered, and the testing accuracy has reached close to 100%, indicating all disease variation has been explained. Thirdly, the future importance analysis suggests hub genes are not the most important for the predictive performance. In figure A on the right, the horizontal axis represents the degree of a node in the comprehensive network, and the y-axis represents importance that we draw from the predictive model, which is logistic regression. The distribution of dots confirms our observation that the degree of a gene cannot be directly interpreted as its influence in biological network, just like networks from other research domains did, as these hub genes are not the most important features of the predictive model. Further, the feature importance analysis shows important genes distributed across different network components. This suggests each network component captures only part of the phenotype or disease variation. That is why, to explain the variation of the entire, to explain the variation of the entire population, one must put multiple network components together. This project delivers results showing the disease phenotype can be explained by a group of network components consisted of the most significant gene-gene interactions. And feature importance analysis shows important genes distribute across multiple network components. This finding is supported by the improvement in the predictive performance because in research analysis, when you want to build predictive models, it is very difficult to achieve the performance indicated by the red bar, which is 100%, almost 100%. Usually, it's 80% is very good, but we did better. So let's conclude my presentation. Any question is welcome.
There we go. Thank you very, very much.
Welcome.
There we are, and let's see if I'm back up on here. Wonderful. So we do have a couple questions coming up, and we'll start with a couple questions that we had for Eric. The first question on there that we had was, are there any real-world implementation examples of Happy Transformer that are up and running at this point? Anything, I guess, that you mentioned some things in industry and things like that, maybe?
So Happy Transformer is under a open source license, meaning anyone can use it and they don't necessarily have to give attribution to the public or even to me. They're allowed to just use it. So I don't know how many or if any people are using it in like real world production scenarios. I was messaging with someone once who was asking me questions about using it to correct incoming audio that was being converted into text. So it sounds like they were converting incoming audio to like speech to text, but then they wanted to run like mask word prediction over their conversion to try to detect if any of the words were out of place. So that's a great example of, and I don't know if that ever made it to production. Then I also saw like on GitHub some team called like LyricsNet. They it might have just been for a hackathon, but they looks like they published a little web framework, a little website that allows people to generate lyrics. And they mentioned that they used Happy Transformer publicly. So it looks like it has been used. I don't know exactly how much due to how it's open source, but yeah, great question.
Thank you very much. And yeah, open source definitely makes it more difficult to know with those kind of things, what's going on with them. Another question was regarding your thing. It sounds like it's very optimized for NLP. How easy is it to use the Happy Transformer system for any sort of data that isn't text data?
So to be honest, it's all text data, all of the methods. So mask word prediction, next sentence prediction, question answering, text classification. It's all NLP, all natural language processing, and that's just the focus.
That makes sense.
Oh, sorry, I think the audio cut out. I think you you muted yourself. Oh.
Sorry, it was the space bar was supposed to unmute me, but it wasn't doing its job.
No worries, no worries.
There we go. We had another question. Actually, our next question was for Zhendong. Regarding, they say on slide 8 of your presentation, you're talking about network centrality as one of the measures that was, obviously you end up finding there are other things that are maybe more useful. But they were wondering if you could talk a little bit about what network centrality is.
For sure. For a network consists of many nodes. Network centrality just tell you what other nodes are playing a very significant structural role in the network. For example, in a social network, the relationships bring us together, but those people who have a lot of friendship with others, they are the backbone of the network, because if they leave this network, people will be isolated into different isolated social groups. But the hub person will bring together different social groups. That is what one of the centrality, which is degree centrality, is doing.
Excellent stuff. Excellent stuff. We'll wait another moment in case anyone else has any questions that they're typing up. And otherwise, I'd like to thank both of our panelists for their excellent presentations, and remind everybody that after all of this, we will have our final closing remarks. And part of that will be, it'll be an open meeting where anyone can speak. And we'd like to get a little bit of feedback on the conference, on the different parts that we did and how that kind of came together, how people feel about the different parts of the conference. And we'll also be giving out the awards at the end as well. I'm just checking, and it doesn't look like we have any additional questions just yet. So I think we're good. So we'll reconvene in 15 minutes. The final Zoom link, that one's just an open meeting. And we look forward to having you guys there. Thank you very much again.
Thank you very much.